right, let's talk about something that's on a lot of network engineers' minds. How do you bridge the gap between your good old traditional switched network and the powerful modern Cisco ACI fabric? If you're planning a migration or even just connecting these two worlds, getting the details right is a really big deal.
Here's what we're going to cover in this explainer. We'll kick things off by looking at the fundamental differences between these two architectures. Then we'll dive right into the nitty-gritty, the specific challenges and solutions, from handling external endpoints to taming spanning tree. And we'll wrap it all up with the key takeaways you need to nail your design.
Okay, let's get right into it. Before you can connect these two systems, you first have to really understand them and appreciate just how different their core philosophies are. We're talking about two completely different ways of thinking about networking.
So, on one side, you've got your classic switch network. It's all about spanning tree protocol, right? BPDUs, route paths, blocking ports, all to prevent those nasty loops. And then you have ACI, a whole different beast. It's a modern leaf spine fabric that uses a Layer 3 IP network underneath it all. And remember, in this world, every external device, including your legacy switches, has to plug into a leaf switch.
And this picture right here, this really nails the problem we're solving. You can see all the core integration points and the challenges we're about to dig into. We've got endpoints that aren't plugged right into the fabric. We need our port channels. We have that crucial and sometimes tricky interaction with spanning tree. And of course, the constant threat of creating a layer 2 loop if we get just one little thing wrong.
So first up on our deep dive, what happens when your endpoints, your servers and PCs aren't plugged directly into an ACI leaf switch? How does the fabric even learn about them? And more importantly, what can go wrong? This is a big one to wrap your head around. Since the traffic from these external devices has to cross that old-school Layer 2 network first, there can be a bit of a delay. A delay in how quickly ACI learns where an endpoint is, or even a delay in noticing that something in the external network has changed, like a failed link. Now, by default, ACI is built for crazy efficiency. It has this really clever feature called Spine Proxy that's designed to stop flooding unknown traffic all over the place. It tries to be smart about it, proxying ARP requests and dropping unknown unicast packets. But here's the catch. That very optimization can cause huge headaches when you're connected to an external network. So picture this. A link in your old network fails. Spanning tree does its thing, figures out a new path, and life goes on. ACI sees that link go down and, correctly, it clears all the endpoints it had learned through that path. But now, another device tries to send traffic to one of those endpoints ACI just forgot about. To ACI, this is unknown unicast traffic, and with Spine Proxy turned on, ACI just drops it. It's gone. You've just created a temporary but very real traffic black hole.
So how do we fix this? It's actually pretty straightforward. For any bridge domain, any BD, that is going to talk to an external Layer 2 network, you have to change the default behavior. You need to go into that BD settings and change Layer 2 unknown unicast to flood. And you also need to check the box for ARP flooding. This basically tells ACI to act a bit more like a traditional switch in this specific context, making sure that traffic always finds its way during a reconvergence.
And, of course, you're still going to want to use link aggregation for more bandwidth and redundancy. The good news is ACI fully supports standard LACP port channels and virtual port channels, or VPCs. The one key difference you have to remember is that with ACI, the VPC peer link isn't a dedicated cable you run between two switches. The fabric itself is the peer link. Okay, now for what is maybe the most important part of this whole puzzle, the translation layer. How does ACI take the VLANs you know and love from your external network and map them to its own internal language, these VXLAN identifiers, to move packets across the fabric?
Now, this slide lays it all out for us. To understand this process, we need to get familiar with three key identifiers. You've got the access VLAN that's actually on the wire, then there's an internal mapping called the FD VLAN, and finally, the fabric VXLAN, which is what actually carries the traffic across the spines. Let's start with the easy one, the access encapsulation VLAN. This is just the standard 802.1q VLAN tag you've been using for years. It's what you configure on the trunk port that connects your old switch to the new ACI leaf. Simple as that. All right, next up are the BD VLAN and FD VLAN. The best way to think of these is like little internal temporary sticky notes that are only meaningful to that one specific leaf switch. The switch uses these as a middle step to translate from the outside world's access VLAN to the internal, fabric-wide VXLAN.
This table, which is a direct output from a leaf switch, shows this in action perfectly. You can see the external access VLANs, 2110 and 2111. The switch internally maps them to these local FD_ VLANs, 41 and 42. Both of them are part of the same bridge domain, which itself has its own unique Fabric VXLAN ID. And this right here, this is the magic of ACI. Look closely at this. The same external VLAN, 211, is connected to two different leaf switches. On leaf 1, it gets mapped to internal FD_VLAN 41, but on leaf 2, it gets mapped to FT_VLAN 28. See? The local IDs are totally different, and that's okay. What matters, what makes it all work, is that they both translate to the exact same fabric-wide VXLAN ID, 9201. That's the secret sauce that allows seamless communication across the entire fabric. And for all you CLI junkies out there who want to see this for yourself, you can just SSH into any leaf switch and run the command show system internal EPM VLAN all. This command is your window into this whole translation process. It'll show you the access VLAN, the internal VLAN type, and the final Fabric VXLAN ID, all in real time. All right, let's switch gears and talk about everyone's favorite protocol, spanning tree. We're going to look at how ACI, a fabric that was literally designed not to need spanning tree, can safely play nice with an external network that completely depends on it to stay alive. The most important thing to get here is that ACI does not play the spanning tree game. It doesn't generate BPDUs, it doesn't try to become the root bridge, none of that. Its only job is to be a big, dumb, transparent wire. It needs to take the BPDUs it gets from one external switch, pass them through the fabric untouched, and send them out to another external switch, letting them figure out the loop-free path on their own. Now here's where it gets a little more nuanced. This BPDU forwarding is a bit different from the general data flooding we set up in the bridge domain earlier. BPDUs are handled specifically within the context of an endpoint group, or EPG. This is really smart because it makes sure that BPDUs for a certain VLAN only travel between the ACI ports where that VLAN is actually supposed to exist, which is exactly how spanning tree expects things to work. This diagram shows a classic gotcha that can take your whole network down. In this example, somebody assigned the same VLAN, VLAN 20, to two different EPGs. Because they're in different EPGs, ACI gives VLAN 20 a different internal VXLAN ID for each one. And what's the result? A BPDU that comes in on VLAN 20 to EPG 1 can't cross the fabric to get to EPG 2. The two external switches are now completely blind to the physical loop between them. A broadcast storm isn't just possible, it's guaranteed. So the rule to live by to prevent this nightmare is super simple, and you can't break it. Within a single bridge domain, which is your layer 2 flooding domain, any single VLAN can only belong to one EPG. That's it. One VLAN, one EPG. Burn that into your brain. Okay, we've got the fundamentals down pat. Now let's dive into some of the trickier, more advanced, real-world stuff. We'll start by looking at networks running multiple spanning tree, or MST, and then we'll look at what is, without a doubt, the #1 cause of spanning tree problems in ACI integrations, how you design your VLAN pools. Now, MST throws a little curveball at us. Unlike regular spanning tree, it sends its BPDUs untagged on the native VLAN. And here's a problem. ACI ports, by default, are set up as trunks, and they expect tagged traffic. So when they see these untagged BPDUs from the MST network, they just drop them. Spanning tree is now broken, and you've basically just invited a loop to your party. So the fix is to give ACI a little help. You have to create an EPG specifically for that native VLAN. Then you apply that EPG to the physical port that's connected to your MST network. And this last part is the most important step. You have to set that port's tagging mode to access 802.1p. This is what tells the ACI leaf, hey, it's okay to accept untagged frames on this port, allowing those BPDUs to get through correctly. ACI also has a pretty smart way of handling topology changes in the outside world. When an external switch sends out a topology change notification, or a TCN BPDU, the ACI fabric actually intercepts it. It uses that as a signal to go ahead and flush the MAC addresses it knows about for that VLAN. This helps the whole system converge much, much faster and helps prevent that black holing issue we talked about earlier. With MST, though, you have to do one more thing. A TCN in MST land refers to an instance number, not a specific VLAN. So you have to manually tell ACI which VLANs live inside which MST instance. You do this by creating a special STP policy with all those mappings, and then you apply that policy to the leaf switches. That way, when ACI sees a TCN for, say, instance 1, it knows exactly which VLAN's endpoints need to be cleared out.
Okay, I need you to pay close attention to this one. This is probably the number one most dangerous and easiest mistake people make, and it is catastrophic. As this diagram shows, if you create two different VLAN pools and they both happen to contain VLAN 10, and you apply them to ports in the same external spanning tree domain, you've just created a ticking time bomb. One port maps VLAN 10 to VXLAN 8001, the other maps it to 9010. Spanning tree is now completely broken, and a loop is going to happen. The way to avoid this nightmare is simple, but you have to be disciplined about it. If your external switches are all in the same spanning tree domain, then all the ACI ports they connect to must get their VLANs from one and only one VLAN pool. That's what guarantees VLAN 10 always maps to the same VLAN ID everywhere, keeping BPDU forwarding consistent and your network loop-free.
All right, that was a ton of information, I know. So before we wrap this up, let's just boil it all down to the most important design principles. The key takeaways you absolutely need to remember to have a successful, stable, and loop-free integration. First things first, flooding. For any bridge domain that's going to touch an external switch network, you must override the defaults. Set L2 unknown unicast to flood and enable ARP flooding. This is your non-negotiable first line of defense against those nasty traffic black holes.
Second, spanning tree. Remember, ACI will forward the BPDUs for you, but only if you configure it correctly. Stick to that golden rule: one access VLAN, one EPG per bridge domain. And if you're dealing with MST, don't forget you have to explicitly account for those untagged native VLAN BPDUs.
And last, but honestly, the most important of all, your VLAN pool design is everything. It will literally make or break your spanning tree integration. One single, non-overlapping VLAN pool for each external STP domain. That is the unbreakable rule for a stable network.
So we've laid out the toolkit, the technical details, and the critical rules of engagement. When you understand these principles, you can sidestep all the common pitfalls and build a really robust, high-performing integrated network. The only question left is, how are you going to apply these principles to your own design?